Welcome. My name is Antoine Pelisse, and I'm a software engineer at Google. And I'm going to talk to you today about how apply works and doesn't, and how hopefully server-side apply will save us all. So today I'm going to talk about declarative configuration a lot because I think it's very, very important to how Kubernetes works and how foundational it is to its success and how it's going to be successful in the future. And so after describing what declarative configuration is, I'm going to talk to you about the implementation that we have in kubectl, which is how we initially implemented the mechanism. And then I'm going to talk about some of the limitations that we found and how we tried to solve them with server-side apply. So what is declarative configuration and why is it so important? I think Brian Grant described it very well in 2014 when he said that we want to support management of services via declarative configuration. I want to show that this is foundational to Kubernetes. This is back in the days, very at the very beginning of the project in 2014, and this is key to Kubernetes and how it's configured. In my opinion, Kubernetes is not just about configuring workloads on the cloud. It's very much about how configuration works and how you decide what you want the system to look like. And so I'm going to focus on that specifically today. So what's declarative configuration? We can see on the left, we have a configuration written as YAML. And this is declarative. Why is it declarative? It's declarative because we do not specify how the number of replicas, for example, in this example, is supposed to change, but we describe what the value should be. So if your system has currently one pod and we apply this configuration, we know that we want to increase the number of pods by 2. But this is not how we describe it. We don't describe the fact that you have to increase the number of replicas by 2. We describe the fact that we want to have 3. And this is very important. This is very important for many reasons. One of them is that this is repeatable. We can do the same thing again and again without knowing about the existing context of the cluster. And so this is going to apply to any cluster in the exact same way. So for example, if you want to recover from a broken cluster, you're going to just have to reapply that configuration that you know works well, and it's going to go back to that state that you know is good. If you want to share the configuration with someone, they can apply the configuration and they're going to have the same state, or at least they should have the same state. It's very, very typical for people in companies to want to create testing environments, and they usually want their environments to be very similar for production and testing so that they know they're testing the right thing. And so, again, repeating the production cluster into a test cluster is very, very convenient and frequent. Migrations, obviously, if you want to migrate from one cloud provider or from one cluster to another, that's very convenient that this is repeatable. Because this is text and because this is easy to read, it's very easy to review and commit to a Git repository. So this is very much done for the GitHub workflows where you push the change to a Git repository and then it's reviewed by your peers. It's easy to review because we don't care about the context or the current state of the cluster. We only care about what you want. You want 3 replicas. Is that a good value or not? The person who reviews doesn't need to know anything else that is this the value you want. And it's also easy for tools to validate, for example, because they can just parse this file, look at the value of replicas and make sure that it validates a specific policy. So you could have a policy that says, we must have the number of replicas bigger than 3 and less than 10. And here it's very easy to write a tool that is going to parse this YAML, look at the number of replicas, and make sure that it validates that policy. Because it's repeatable, it's also very easy to roll back. And Git typically provides this kind of workflow. So you just have to revert your commit, go back to a state that you know works well, and hopefully everything is going to go back to a good state that we know works. I'm going to emphasize specifically that this is what I call data. And why do I call this data rather than code, for example, is that this is very easy to parse, deserialize, and serialize in any common language. If we were to use Python for the configuration, I claim that it would be much harder for any language to be able to parse that. It's very difficult in any language, and let's say JavaScript, for example, to parse Python, look for the replicas field, see that the value is actually a statement, which may be a function, for example. And then if you want to see what the value is, you have to evaluate this statement, which you can do in JavaScript if the statement is Python. There is no Python parser written in every language that we know of, but there is a parser for YAML, hopefully in most languages, and they're usually very easy to use. And changing a single value is typically very easy. So now, if you want to write a tool that is going to look for this value, it's much easier than if the configuration was written as Python or any other language. To be honest, typically languages are not easy to parse. This is very convenient for collaboration because we want people to collaborate on their configuration, and we want people to collaborate with machines on their configuration. And so we want people and tools to be able to look at the config, make changes, validate, update as needed based maybe on a state that would be continuously reconciled. And so an example of that would be a horizontal pod autoscaler, which would look at the state of your cluster and update the value of replicas based on the workload on the cluster to suit the current needs. There are challenges with declarative configuration, though. There is no typically endpoint in CRUD APIs for declarative endpoints. You can create, you can read, you can update, you can delete, but there is no way to say, hey, this is what I want, this is what I care about, just do the right thing, do what I need. There is no such thing with CRUD APIs. So one example of that is that we don't know if the resource needs to be created or updated. You have to look, does this resource exist? If it doesn't, then I'm going to create it, but then you can have a raise condition. This is much more complicated than it looks. If you want to update the resource now, it's difficult because typically update in a CRUD API is going to replace the entire object. And if you only care about specific fields, and because we want it to be collaborative, you probably only care about some specific fields. Maybe some controllers care about other values in the same object. So we never want to replace the entire object. So we want to merge them. For that, we have patch, but patch is very imperative in nature. You have to look specifically at the changes that you want to make and then apply them. There is JSON merge patch that does that, but it doesn't work very well on lists. Kubernetes has tons of lists for many reasons. It uses associative list, as you know. This is the type of list where the name is actually the key. There are map hidden inside a list. And JSON merge patch just replaces list altogether. If you apply a list in JSON merge patch, it's going to replace the entire list. So if a controller has added anything to the list, it's going to be overridden. So all of that to say that basically it's very hard not to hinder collaboration when creating such a system. The initial implementation of kubectl apply is written on the client and tries to address some of these challenges. Here we can see from this tweet that kubectl apply is the solution to what I just described. It's the declarative configuration tool. It allows you to repeat. You can take a cluster, make some changes, apply them to a different cluster, and hopefully everything is going to just work. This is obviously very different from reality where you have storage and clusters are typically slightly different from each other. So you need to have some adjustments, but basically this is the idea. It's still much easier than taking a lot of code to generate the config and make sure that it applies properly to a different context. So how does this work? How do we apply? We do apply by running kubectl apply command, the command, and you can apply these to many configurations. This is convenient because, again, we don't have to look at each individual configuration and decide if they need to be created or updated. This is obviously not meant at all for imperative commands, like you can't apply a charge credit card or open this door. Though if you wanted to do open doors, you could rephrase this and say door open, and that would be either true or false, and this would automatically become declarative. Um, this is much more collaborative too because it allows to change only specific fields rather than replacing the entire object. We'll see in the next slide, but basically kubectl apply sends a patch, and it's literally trying to look at each individual fields, see which ones have changed, and update the object by sending a patch to change these values. The way it decides on what has changed and what needs to change is based on what you had applied before. And so for that, we save the object the way you had it before in the object itself under this last applied annotation. So as you can see here, we have the entire object that we've seen before inside the annotation saved in the object. This is literally how we save the old configuration in Kubernetes with kubectl apply. How does it work? So we can see on the left that we get the object from the server, and we can see that the number of replicas is 5. The image is nginx 114.2, and it has a sidecar container, and I've removed the details of the sidecar because they're not relevant here. But we can see that there is a sidecar. And we can see the before, which is coming from the annotation, that we had 3 replicas before, and so probably someone must have changed that value since we applied last time. And the image hasn't changed. We can also see that we didn't apply the sidecar initially. So someone must have an opinion about this sidecar, but it's definitely not us. And then we can see what is being applied now in the third column. We still want 3 replicas, and we want to update the image to the nginx image to 114.3. We are going to look at these 3 different objects, the current version, the before version, and the applied version, and we're going to perform a 3-way merge. We're going to compute this new final object, which has the number of replicas equal 3, which is the value that you said you wanted. We're going to update the image to nginx 114.3 as you wanted, and we're going to conserve the sidecar container because you don't have an opinion about that, so we don't believe that it should be removed. Once we have this new object, we are going to compare it with the existing object, compute the difference, and send that difference as a patch to the server. All of that sounds good, but obviously there are limitations with this system. The patch that we use to send to Kubernetes has been made by the Kubernetes community as the needs were coming. We made it in a very homegrown way without thinking about all the problems we could have with that. And obviously we missed many use cases, and it became insanely hard to update. So one of the problems with the patch strategy that we created that is called a strategic merge patch is that if we need to make an update to the strategic merge patch, we don't have a way to version the strategy. So if we update the client, then we also need to update the server, but we also need to make sure that the server and the client match and that they use the same version. And if they don't, then we need some sort of mechanism to know if they use the same version or what version they can use. And we don't even know the version anyway. So this was very, very complicated. We needed to make the changes over many versions of Kubernetes. Any change required 2 or 3 releases to make sure that we could propagate the change everywhere. And this was very, very complicated. So knowing that this was never going to be the good solution anyway, we never implemented it for custom resources. So that doesn't even work for custom resources. You can kubectl apply custom resources, but you miss a lot of the possibilities that are available to you if you're using a built-in type. It also has limitations on the collaboration, to be honest. It's not solving all the use cases of collaboration that we had in mind. And specifically because the implementation, which is very complex, is specifically made in kubectl in Golang. And if you want to use any other language than Golang, there is no way for you to reuse the algorithm. You can maybe create a new process and fork to kubectl, but that's the only way. You can't easily create a tool or a library that is going to use apply if it's not written in Golang or if it's not using the kubectl binary. And that's really detrimental for the ecosystem. One of the other challenge is that only one actor can apply. So because we have this annotation that says this is the last thing that you applied, no one else can come and use the same annotation, obviously, because they would just not agree. Um, so we could create maybe another annotation, but clearly the people would take the chance and just override their fields constantly. If you have an opinion about a field and I have a different opinion about the same field, anytime I'm applying, I'm going to overwrite your change. And anytime you apply, you're going to overwrite my change. And we're going to keep fighting like this in a way that is sometimes hard to detect. And sometimes, even if it's easy to detect, you might detect it because you've broken your cluster. Um, so the fields being overridden unintentionally is definitely a big problem for collaboration. One very good example of that, again using the replicas field, is that if you, let's say you created a deployment with 3 replicas, and later on you want to use an HPA to decide automatically how many replicas you want. And let's say your system is very successful and you end up having 1,000 replicas. And now when you apply your config, you actually apply 3 by mistake. It's going to override this field, the 1,000 replicas, and you're going to end up with only 3, which may very well break the system and your customers' use cases. So that's actually quite a terrible bug that we want to avoid. Um, Finally, one of the problem we had with this approach is, again, we didn't know exactly where we were going to end up when we started, and so because of this lack of systemic approach, there are many bugs that are very subtle and hard to fix. And an example again about these replicas, and to take the same example, if you had this HPA set the number of replicas to 1,000, and you actually remove it from your config because you don't want to override it. So you remove it from your config and apply. It's actually going to believe that you want to remove the replicas field. And the problem is when you remove the replicas field, it gets defaulted to 1. So you break your customers anyway. So there is actually no way, or only very complicated ways to solve this problem. If you want to remove the replicas field, it's probably going to break something. And this is very complicated and unfortunate. So we invented server-side apply, which is a new mechanism for applying to a cluster. This works by removing every logic we have in kubectl and move it to the server. So literally, we're stripping kubectl from any apply logic, any merge logic, and we're moving it to the cluster with some changes. And so what do? We created a new endpoint on the API server where you can send your intent and say, this is what I want, and this is what I care about. Please do so. Do not override anything that I'm not specifying in there. If I've removed anything, don't break everything, please. And the server is going to take care of all of that. It's very, very convenient because now you can write a client without doing anything. You just have to send the object. You just read the file, send it to the proper endpoint, and it's going to be applied to the cluster. It's as easy as doing curl. Curl send this file to this specific URL, and boom, you have the file merged on the server properly. We've been very careful to keep some compatibility with client-side apply, and so you can still use these mechanisms and client-side apply at the same time. And this is still going to work. We're going to be very careful to maintain the last applied annotation as you do, and you can go back and forth so that things still work the way you would expect. And if you want to go back and try one and go back to the other one, it's still going to work. So I think that's a very good feature. How does that work? Well, because we want the collaborative approach, we've decided to create managers. So managers are actors of the system. We believe that configurations have many actors acting on the same configuration, and we want them to work together well and prevent any problem that could happen if someone is trying to change a field that you have an opinion about. So each actor in the system has a name. As you can see on this on the left, we have the manager who is kubectl in this case, and each actor has a list of fields that they manage. It's actually not a list; we could call it a set. It's a set of fields, and these are the fields that we believe you have an opinion about. So if you apply the configuration that we saw before, you're going to have an opinion about replicas, you're going to have an opinion about the container image and the container name. Um, if someone else has an opinion about the same fields, you're going to get a conflict. So what happens is that if somebody, for example, the HPA has set the number of replicas to a different value, we're going to notice that they already care about that value. And so as you're trying to change the value of the field, we will send back an error saying someone already has and manages this field. They have an opinion. Are you sure you want to change their value? Because that can be catastrophic if you do. And so the user has two options. They can decide to remove the value from their file, in which case they can then reapply and they're not going to get a conflict because they literally said, yeah, indeed, I don't have an opinion about replicas anymore. Let the system decide. Someone else has an opinion. I trust them to have a better opinion than I. Let them do it. Or you can use the force flag, which is going to force the value. And in this case, we're literally going to take the value of replicas from the manage field of the HPA. We're going to take it from them and we're going to put it back in the fields that you manage. One interesting feature, again, is the backwards compatibility that we want to maintain. We can't start breaking things that work today in Kubernetes, including controllers. It's difficult when there is an error in a controller to know about it and for a user to do anything about it. So controllers are always sort of forcing, and they're not using apply anyway because apply is new. So, but even if they're not using apply and even if they're not forcing, we always accept their changes, and we only detect that they have a change because we can look at the difference. So if the HPA changes just the replicas, it's going to own just the replicas. And we know that because it changed the value, and whenever you change the value, it's because you have an opinion. And that's how we build the sets for controllers and types that did not know about server-side apply or do not use server-side apply before. So we are completely maintaining this backward compatibility with existing workflows, and we're just doing the right thing by detecting that they have an opinion because they changed something. So now the question is, how are objects merged? We've tried to keep the logic as simple as possible. And by that, I mean, we literally take what you apply, we take the existing object, and we put it on top. So any value that you specify is going to end up in the object, and any value that you haven't specified is going to be kept the same. Obviously, one of the questions when we do that is how do you remove a field? Because if you remove it from your config and apply it, well, it's not going to be removed. It's going to keep the current value. And so for that, we just remove the fields if nobody has an opinion about it anymore. So if no one has an opinion about replicas, we just remove it. And what happens when replicas is removed, it goes back to 1. But it only happens if no one has an opinion. So if you remove it from your config, but the HPA has set a value, we are going to know, oh, well, the HPA still cares about that. Let's keep the value because we believe it's correct. How do we keep track of who owns what? I've discussed it a little bit before. So for controllers, we typically look at what has changed. When you apply, we look at all the fields that you have applied, and we create a set, a mathematical set of all the fields that you care about. And at that time, we look at all the manager sets in the list, and we intersect them with your set. And any intersection that comes as non-empty shows the conflict. So we literally take all of these sets and we send them back to the user saying, you have an intersection with this other person, which means you care about the same field. You need to do something about this. And as you could see before, we actually save the name of the person, and for some changes, we also keep the date so that we know when someone changed the field that you're trying to edit. So we can say, hey, you're trying to change the field that the HPA has set at this value. This is also very important for the out-of-band changes. So let's say something is broken in your cluster and someone goes and connect and directly edits one of the field. When you reapply, maybe you're going to override that value. And we obviously don't want to do that, because if you do that, your cluster is going to break, right? Um, and so at that time, you're going to see a very nice conflict that says, you are trying to change this field set by this person. Are you sure you want to do so? And reasonably, you should ask yourself if this is what you actually want to do. Um, Also, finally, this works for built-in types and custom resources. We're really trying to make custom resources work the way built-in types work. And for that, we've tried to make everything look and behave as closely as possible. So if you are writing a custom type, all of these should work exactly the same way as it would if you had a built-in type. We don't want you to miss out on any feature. What are the benefits of that? So it enables the ecosystem because it's so much easier to write, apply, um, that it's much easier to write a new tool. You don't have to write any logic. You just have to send the content to the API server. So now, if you want to write a tool, it's a few lines of code just to update the object, which is a massive change compared to today, where you had to either use Go or use the kubectl tool, make sure it's shipped properly, that the version is right. Uh, this is much easier now. Obviously, the other change is that we are more collaborative. You have multiple players. We are starting to convert some of the existing controllers to use this mechanism because we believe it has benefits and it's much easier to implement and maintain. The friendly user, the friendly errors are much better and prevent you from breaking your clusters accidentally. And of course, it improves the human and machine collaboration because um, you can now change parts of the config while the machine changes other parts of the config without interacting with each other and without overriding the values that you don't want to override by accident. Now, now that we have that, so we know that we can apply a lot of configuration, but I suspect you're soon going to realize that you have too many configuration files. It's very common for people to wonder what to do with all of these YAML files, and I'm sure you've seen that before. You have too many YAML files. I've had this problem, and often you have one version of the file and you want to apply it for maybe a test environment, as I talked about before. The problem is that the test environment is not the exact same environment as the production. You want to use a different database. I mean, hopefully. You have different requirements. You probably don't want as many pods. You probably don't want it to be deployed to the same place. There are many things that are actually different between the test environment and the product environment. And so you have very small variations between these configurations that can be already made of like many different files. And if you just want to change one value out of these many different configurations, you're going to have this problem. And it starts very quickly. Even having two configurations is already too much for me. So I have this problem constantly. What we've made is that we've created customized because we believe it's as close as possible to the principles that we've described in this presentation. We believe that Customize is collaborative. It lets you share the configuration easily, but it's also data. So I still believe that the configuration should be data. And this is very difficult because it's very tempting to use a programming language to abstract away some of this redundancy. But I suspect there is something wrong because as soon as the configuration becomes code, it's not possible to collaborate with machine. I do not believe that it's possible to have configurations written as code if you want machines to edit them. Um, so that's one of the big challenge that we have today. And Customize is one of the solution, but it has other limitations. I know so many solutions exist out there, but most of them do not treat the configuration as data and as collaborative as it should be. And I think that's one of the problems that we'll want to save. We'll want to fix for later. That's it for me. That's all I have for today. Thank you so much for listening.